Good afternoon, everyone. Thank you for joining this session. My name is Chen Xia, and I'm here representing Cohere. Today, I'm excited to share with you how we've been optimizing our inference stack to serve our Command A models efficiently use vLLM. This talk will cover the technical innovations we've implemented to make enterprise-scale language model serving both efficient and cost-effective. So before we dive into the details, let me quickly introduce Cohere for those who might not be familiar with us. Cohere is an enterprise language AI platform with a mission to empower developers and enterprise to build products and capture business value with language AI. On the product side, we offer North, which is our secure AI workspace platform for enterprise productivity, and Compass, an end-to-end search system designed to surface contextually relevant information. What's particularly important for our enterprise customers is our flexible deployment options. We support API access all major cloud platforms, including AWS, Azure, GCP, and Oracle, plus private cloud and on-premises deployments. Our model lineup includes the Command A family for text generation, reasoning, vision, and translation, embedding models for semantic search and embedding across over 100 languages, and re-ranker models for improving search quality and relevance. We were founded by Aidan Gomez, who's our CEO, along with Nick Frost and Ivan Zhang. We maintain a global presence with offices in Toronto, San Francisco, New York, London, Paris, and Seoul. And we are hiring across all of those locations. Now let me tell you about our team. We are a small but nimble model efficiency team that supports the entire company's inference stack. Despite our size, we cover a lot of ground. Our work falls into three main areas. First, compute. This is where we handle multiple hardware platforms. We develop kernel support for different precisions, design scheduling strategies, and build theoretical performance models for various architectures. Second, quantization. Here we develop quantization recipes and validate accuracy across different evaluation sets. This is crucial because quantization can dramatically improve a serving efficiency, but only if we maintain model quality. Third, efficiency algorithms. We explore cutting-edge techniques for both prefilling and decoding, like speculative decoding, and we develop efficient algorithms specifically for structured output and tool use, which are increasingly important for enterprise applications. So let me quickly walk you through our Command A model series. We have 4 specialized variants: Command A for general purpose text generation, Command A reasoning for complex reasoning tasks, Command A vision for multi-model understanding, Command A translate for high-quality translation. All these models are available with open weights on Hugging Face. You can find them in our collection. I've included a link here in the presentation for those who want to explore them later. So let me focus on Command A for a moment because it really embodies our design philosophy. Scalable efficiency is at the core of Command A. With a serving footprint of just 2 A100s, 80 gigabytes, or H100s, it requires far less compute than comparable models on the market. This isn't just about cost. For primitive deployments, this efficiency is absolutely critical when enterprises can't afford massive GPU clusters. So this makes advanced AI accessible. Look at the inference efficiency chart on the right. You can see Command A achieves 158 output tokens per second at 1K context rollout, significantly outperforming both GPT-4 and DeepSeek V3. On the enterprise-ready capabilities side, we support 256,000 context lengths, which enables robust RAG with verifiable citations, agentic tool use, enterprise-grade security, and strong multilingual performance. The benchmark results at the bottom show that Command A performs competitively or better than both DeepSeek V3 and GPT-4o across academic benchmarks like MMLU and math, agent tasks, and coding challenges. This demonstrates that efficiency doesn't mean sacrificing quality. Command A reasoning takes things a step further with advanced reasoning capabilities. Looking at the agentic benchmarks on the right, you can see we outperform GPT-OS 120B, DeepSeek R1, and the Mistral's Magistral Medium across general tool use agents, customer service agents, and multilingual agents. What's really innovative here is our hybrid reasoning approach. Instead of maintaining separate reasoning and non-reasoning model, we use a token budget system that lets you directly manage compute usage and control costs. This is a game changer for production deployments because you can dynamically allocate more reasoning tokens for complex queries and fewer for simple ones. And deep research benchmark results at the bottom confirm this works across multiple dimensions: overall performance, instruction following, readability, insight generation, and comprehensiveness. And importantly, this isn't just a research prototype. Command A reasoning is production ready and actually powers North, our secure agentic AI platform. Command A Vision extends our capabilities into the visual domain with 3 key strengths. First, chart, graph, and diagram analysis. You can see in the query examples how we can create markdown tables from charts, convert invoices to JSON, and analyze building damage from images. Second, document OCR and visual processing with results showing chart QA, doc VQA, and OCR bench. We are leading in this space. Third, the real-world scene understanding. The performance tables on the right demonstrates that Command A Vision is competitive with or outperform models like GPT 4.1, Pixtral Large, Mistral Medium 3, and Llama 4 Maverick across these diverse vision tasks. Command A Translate rounds out our model family with support for translation across 23 widely used business languages. The chart on the right shows our machine translation quality scores on WMT 24++. You can see Command A Translate significantly outperforms major competitors. This level of quality is essential for enterprise customers operating globally. So let's get into the technical details. Understanding the architecture is crucial to understand our optimization strategies. Command A has 6 key architectural designs. Interleave sliding window attentions. We mix sliding window and the full attention layers in a specific pattern. Rope to nope and back again. Nope is like no rope. So nope on full attention layer and rope on sliding window attention layer. Parallel transformer block. Processing attention and the FFN in parallel for better hardware utilization. No bias, simplifying the architecture and reducing memory footprint. GQA, reducing the KV cache size, and the share input and output embeddings. That is a further parameter sharing memory optimization. So looking at the diagram on the right, you can see how we structure our transformer blocks. We alternate between SWA blocks, sliding window attention shown in pink, and the full attention blocks. This interleaving is key to balancing performance with efficiency. What's particularly gratifying is that since we launched earlier this year, many models have adopted similar designs, including Llama 4 and GPT-OSS. This validates our architectural choices. Let me dive deeper into one of our most important designs, interleave sliding window attention. The key design elements are sliding window size of 4096. This is the local attention span. Interleave the pattern with 3:1 ratio. For every full attention layer, we have these 3 sliding window layers. This leads to 75 memory saving with massive throughput increase. Preserve the long context performance while freeing up KV cache space. Looking at the diagram on top right, you can see how each token attends to a limited window. The key insight is that not every layer needs to see the entire sequence. Most layers can work with local information. The performance chart at the bottom shows Ruler V2, which came out recently. Performance across various tasks from 8K to 128K context. Notice how we maintain strong performance across different context lengths while using significantly less memory. The yellow bars shows our causal dense configuration performing comparably to models using full attention, but with a fraction of the memory cost. This is absolutely critical for serving long context models efficiently. In production, memory is often the bottleneck, not compute. By reducing KV cache by 75%, we can serve many more concurrent requests on the same hardware. To actually leverage our interleaved attention architecture in production, we need a customized memory allocator. This was one of our most significant engineering challenges. Let me walk you through our key design decisions. First, our assumption is we use a fixed embedding size. Each layer has the same D type, and we maintain an exact 3:1 ratio of sliding window to full attention layers. Second, the grouping strategy. For command A, it has 64 layers, so 48 sliding window and 12 full attention. We organize them into 5 groups. Looking at the table on the top right, you can see how tokens 0 to 15 go to blocks covering 4.0 through 4.9. Then subsequent token ranges are assigned to different sliding window groups. The beauty of this is no padding is needed, so there's no wasted memory. Third, prefix caching. This is where things get really interesting. We leverage the intersection between full attention and sliding window attention to maintain high caching hit rates. The diagram at the bottom right illustrates this. For the full attention layers, we cache tokens 0 to 6, and for sliding window layers, we calculate which tokens under that window length can be cached. For those who want to dive deeper, we've collaborated with the community on Jenga, which offers even more flexible embedding sizes and better cache eviction policies. There's also a great vLLM office hour session covering this in detail. This hybrid allocator was critical to making our architecture practical in production. Without it, the memory savings from our interleaved attention will be much harder to realize. Another major efficiency technique we've implemented is speculative decoding, which can dramatically reduce latency. Our approach is based on Eagle-1, but without tree attention, making it simpler and more practical for production. The diagram on the right shows our architecture. We have a lightweight draft model that predicts multiple tokens ahead. Then the main transformer verifies these predictions in parallel. Here are our key designs. Sliding window attention on Eagle attention layer, applying sliding window attention even in the draft model for consistency and efficiency. FB8 quantization, the draft model is quantized to minimize its overhead. CUDA graph optimization, minimizing kernel launch overhead, integrated with hybrid memory allocator, ensuring the draft model works seamlessly with our CUDA customized memory management. The beauty of speculative decoding is that it's essentially free when predictions are correct. You are doing the verification work anyway, so any accepted tokens are pure speed up. And even when predictions are wrong, you haven't lost much because the verification is fast. In practice, this gives us significant improvements in tokens per second, especially for the types of coherent structured text that enterprise applications often generate. Quantization is another pillar of our efficiency strategy. Let me talk about our W8A8 recipe. That's a 8-bit weights and 8-bit activations. Our approach is straightforward but effective. So first is static per channel quantization on weights. Weights are quantized once during model preparation. Dynamic per token quantization on activations. Activations are quantized on the fly during inference. The results are compelling, like it has 2x plus throughput and memory savings compared to BF16 with minimal accuracy degradation. I want to give a shout out here. The M compressor kernel is amazing. The work the community has done, particularly the team at Neuromagic, has been instrumental in making this practical. Their kernels are highly optimized and make it easy to integrate quantization into production systems. For many enterprise use cases, W8A8 hits the sweet spot of performance, efficiency, and quality. The quality degradation is minimal enough that most applications don't notice, but efficiency gains are substantial. Now let's talk about W4A16, 4-bit weights with 16-bit activations. This is where things get really interesting from a kernel optimization perspective. Machete, developed by Wilkinson and colleagues, is the state-of-the-art W4A16 kernel on Hopper GPUs. However, when we profiled it, we discovered that memory bound performance, particularly in low batch decoding scenarios, was suboptimal. It wasn't approaching GPU memory bandwidth limits, which was surprising. Through detailed profiling, we found that TMA, which is Tensor Memory Accelerator in Hopper, loads were loading 2x the required bytes. Looking at the profiling data in the top right, you can see the sectors read versus the number of TMA instructions. That is clearly inefficient. The fix, just one line code changes to change the TMA box sizes or the layout. And this resulted in a 30% performance improvement. This is a great example of how understanding hardware details and doing careful profiling can yield huge dividends. The code snippet at the bottom right shows the actual change. That's one line change, adjusting layout to allow TMA to load the full 32 bytes sectors efficiently. We've also extended the kernel to support smaller grouper sizes, all the way down to 64, and asymmetric quantization, making it more flexible for different models and use cases. This work has been merged into vLLM, so the entire community could benefit. Let me introduce you to W4A8, 4-bit weights with 8-bit activations. This is truly the best of both worlds. Well, why W4A8? Weights in 4-bit safe space, reducing memory footprint and bandwidth requirements, while activation in 8-bit let us utilize FP8 compute on modern GPUs like Hopper. This is crucial because Hopper's FP8 tensor cores are fast. The challenge was that there was a lack of performant W4A8 kernels in the open source ecosystem. So we built one using Catalyst, targeting the Hopper architecture specifically. Looking at the quality results and the bottom right, you can see that W4A8 has negligible quality loss compared to both FP8 and the W4A16 baseline across benchmark. The bars are nearly identical. This is exactly what I want to see. So the TTFT chart on the top right tells the performance story. At batch size 1, W4A8 achieves about 2x reduction in TTFT. This is directly due to leveraging FP8 compute instead of being memory bound with int4 math. Even at higher concurrency, like batch size 8, W4A8 maintains a significant advantage. The performance story of W4A8 gets even more interesting when you look at the implementation details. The fundamental bottleneck in mixed precision kernels is converting lower precision weights to higher precision activations. Traditionally, with W4A16, this uses CUDA cores, which is relatively slow. The problem with naive W4A8 is even worse. There is no FP8 scalar math on GPUs. So you'd have to do a roundabout conversion from int4 to FP16 to FP8, which completely kills the performance. The solution from Catalyst upstream is brilliant, a lookup table-based approach that maps int4 directly to FP8 because int4 has only 16 values, completely bypassing the bottleneck. The diagram on the right illustrates this. Scales in FP8 are used to directly convert int4 weights to FP8 values using a pre-computed lookup table, which then feeds into the FP8 tensor cores. However, this kernel requires a specific encoding and weight layout. The naive Python implementation to repack weights took over 10 minutes for large models, which is completely impractical for production. So we implemented a custom CUDA kernel for this repacking step, reducing startup from larger than 10 minutes to less than 1 minute. This makes it practical to serve models with W4A8 quantization in real-world deployments. These kinds of engineering details matter enormously in production systems. A 10-minute startup time might be acceptable for research, but not when you need to scale or respond to failures quickly. Achieving good performance with W4A8 isn't just about kernel, it's about the quantization recipe. W4A8 needs int4 weights and FP8 scales. Our initial approach was to leverage our existing W4A16 workflow, which makes sense since we already have that pipeline working well. However, we discovered that naively casting FP16 group scales to FP8 leads to terrible results. Looking at the top right distribution chart, you can see that the BF16 scales have a nice smooth distribution, but the bottom chart shows that after naive casting to FP8, distribution becomes terrible. Lots of precision loss and bad granularity. The solution was a customized quantization pipeline that's designed from the ground up FP8 scales, not just adapted from FP16. We are currently working with the AM compressor maintainers to open source these recipes. This is important because we want the whole community to be able to use W4A8 effectively. The recipes involves careful calibration and specific techniques to ensure the FP8 scales preserve enough precision for good model quality. So stay tuned for more details. We should have this publicly soon. When serving models across multiple GPUs, communication becomes critical. Let me talk about our communication optimization story. We leverage symmetric memory, which optimizes GPU to GPU collective communication operations by using buffers with identical virtual addresses across all GPUs. Our key conclusions from benchmarking is looking at the charts on the right, you can see that Nickel 2.27 or reduced outperformance vLLM's default implementations. For different message sizes, especially as messages get larger in out-of-place results. vLLM's custom implementation, the green line, is competitive at small message sizes, but starts falling behind at around 1 megabytes and larger. The in-place results bottom chart show similar patterns with Nickel 2.27 and the newer Nickel Ring implementation, both of vLLM's default for larger messages. Our strategy is to choose different communication strategies based on message sizes. vLLM's approach for very small messages, Nickel for larger ones. This benefits TTFT significantly, especially for large batch sizes where communication volumes are high. Let me ramp up the technical discussion by talking about hardware support. At Cohere, we offer combinations of all these optimization techniques across different hardware platforms to support various deployment requirements, both internally for our API service and externally for enterprise customers. For example, we support 256,000 plus context lengths on just 2 H100s. This is huge for making long context serving practical. 256,000 plus contexts on a single B200 or MI300X, even more efficient for next-gen hardware. We are also working on lower-end cards and ASIC accelerators for cost-sensitive deployments. Let's focus on our recent work, B200, for a moment, because this is particularly exciting. Looking at the throughput chart on the top right, you can see Command A achieves impressive tokens per GPU per second, especially with flash infer on B200. Our optimizations for B200 includes leveraging flash infer and TensorRT kernels. These are optimized specifically for Blackwell architecture, minimizing kernel scheduling overhead using CUDA graphs. This is reducing the launching latency or launching overhead. Tuning Nickel symmetric memory, optimizing for the new NVLink configurations on B200. And looking at the speculative decoding chart on the bottom right, at TP8, like tensor parallelism across 8 GPUs, we are seeing nearly 200 TOPS with speculative decoding on B200, compared to about 135 on H100. That's roughly a 40 to 50% improvement. These hardware optimizations matter because they directly translate to lower costs and better latency for our customers. Before I close, I want to acknowledge all the people and teams who made this work possible. First, our inference team at Cohere. This has been a true team effort. The vLLM community has been absolutely amazing to work with, particularly Wusu Kwang, Chen Xia, and Simon Mo. Their responsiveness and collaboration have been invaluable. Red Hat, and specifically Robert Shaw and Lucas Wilkinson for their work on Machete and other kernel optimizations. Our engineering leadership, Bharat and Asir, for supporting the work and giving us the space to innovate. And finally, Guo Liang, an amazing intern who contributed significantly to several projects, several aspects of these projects. This kind of work really does take a village, and I'm grateful to everyone involved. Yeah, I'm happy to take questions right now. Or feel free to catch me after the session. Thank you. Feel free to ask questions.
Yes, position yourself more strongly, or more customers are for your inference platform or your users of the models?
Sorry?
Most of your users or customers are using your inference platform, or they are using your models as such?
Yeah, I think most of them are using our on-prem deployments, and then Azure, GCP, and Bedrock, AWS, like those platforms that we put our models on. And I think we have also have platform support, and it has some traffics, but mostly our revenue or our request is for on-prem deployments from different.
Of your own models?
Yes. Models and North platforms. So it's kind of all-in-one solution that we have our models on-prem, air-gap deploy on your platform with our in-house developed North platform that basically you can think of it connects different sources, doing those workflows, and help you achieve day-to-day tasks. Okay, so I think I can wrap up here.
Awesome. Thank you so much.